Imagine a day when your memories, your thoughts, maybe even, I don't know, your entire consciousness could be digitally backed up. Sounds like something straight out of a sci-fi movie, right?
Yeah.
But what if that day is far closer than we actually think? Welcome to the Deep Dive. Today we're taking a plunge into the fascinating and frankly a little mind-bending world of digital immortality, mind uploading, and these incredible advancements happening in neuromorphic computing. We've gathered insights from a whole stack of sources: Evrim, Ajaka, Bilim Krugu, Kulubu, Perspective, Wikipedia, STM, ThinkTech. Quite a mix.
Absolutely. And our mission for you, our listener, is really to extract the most important nuggets of knowledge from all this fascinating material. We want to give you a shortcut, to being truly well-informed on a topic that doesn't just touch on technology, but goes deep into philosophy, ethics, even what it fundamentally means to be human.
Okay, so let's kick things off. Let's explore the bedrock of this future, the science of connection. Maybe starting with brain-computer interfaces, BCIs. These are systems designed to, what? Read the brain's electrical activity and turn that into computer commands. Is that basically it?
That's right, yeah. It's essentially teaching a machine to speak the brain's language. Our brains are constantly generating electricity because of, well, billions of neurons firing every second. Think of these firings as action potentials, like tiny, tiny rapid clicks. Millions of these happening per second are what create your thoughts, your feelings, every single movement you make.
Right, so it's reading those clicks, but how does that translate into something a computer can use? You mentioned an analogy like a phone's vibration motor.
Yeah, that's a decent analogy. Like, you think walk, your brain sends an electrical signal down to your muscles. A BCI intercepts or reads a similar signal associated with an intention. It says, aha, that pattern means move the arm or maybe move the mouse pointer. And the really fascinating part is we're getting much better at interpreting those signals, not just detecting them, turning them into actual commands.
Okay, and this isn't just theory anymore. You hear about real-world applications, like Elon Musk's Neuralink project. What have they actually shown?
Well, Neuralink has already shown monkeys playing computer games, just with their thoughts. And in 2024, they hit a big milestone, the first human implant. It allowed a person to move a computer mouse pointer just by thinking about it.
Wow. Moving a mouse pointer is one thing, but I heard their next target is helping nonverbal people generate text directly from their thoughts. That sounds like a whole different league.
Oh, it absolutely is. The jump from simple motor commands, like moving a cursor, to translating complex thoughts into language is immense. It requires a much, much more granular understanding of the neural code, more sophisticated algorithms to decode intention, and you had to filter out all the background noise of just general brain activity. It's a huge task, but, progress is being made.
Right. Okay, so moving beyond just controlling things with thoughts, what about the memories themselves? The nature of memory and whether it could be transferred. That's the next big leap, isn't it?
Exactly. Memory at the core is defined as these patterns of connections, synapses between your neurons. And here's the crucial insight. That this isn't just abstract biology. It's the very reason why the idea of uploading a mind isn't pure fantasy. It boils down to potentially replicating these specific, intricate patterns.
Like a blueprint for each memory.
Precisely. Imagine your mind like a massive, incredibly complex Lego set. Each memory, your childhood home, a song, what you had for breakfast is a unique way those Lego blocks are connected, a specific pattern.
And these patterns, they have an electrical signature, right? So scientists can actually read some of them using things like EEG, ECOG, fMRI. These tools map brain activity.
Yes, they map activity by looking at electrical signals or changes in blood flow. And this leads to that surprising, almost sci-fi possibility, like the kung fu loading scene in The Matrix. If we can truly identify and replicate these unique synaptic patterns, then theoretically memories could be copied, maybe even transferred.
And we're already seeing experiments, right? Not quite loading kung fu yet, but simpler stuff.
Definitely. There was a groundbreaking experiment back in 2013 at Duke University. They taught one mouse to solve a maze, recorded its brain activity during the process. Then they transferred that recorded pattern to another mouse. And get this, the second mouse, with zero prior training, was able to solve the maze much faster. It was a clear demonstration of, experience transfer.
Wow, in mice. That's incredible. Has it moved beyond mice?
It has. By 2019, human experiments showed people could type using just their thoughts, and by 2022, they were translating thoughts from non-speech brain regions into text for patients who couldn't speak. The implication is huge. When the signals a brain makes while learning something are transferred to another brain, that person acts as if they learned it themselves.
As if they learned it. That's profound. It really blurs the lines. But okay, this brings us to a really crucial distinction. Memory is one thing. Consciousness,
Yeah.
that feeling of being you,
Yeah.
that's something else entirely, right?
Absolutely. Consciousness is that fundamental feeling of, I am aware, I am me, I'm experiencing this right now. For true consciousness transfer, you wouldn't just copy memories, you'd need to transfer the whole package. Personality, perception, feelings, the subjective qualia, the whole experience of being.
Right. And that's where these more ambitious technologies come in, like whole brain emulation, WBE.
Exactly. WBE is the concept, the goal of creating a 100% faithful digital replica of a specific brain, neuron by neuron, connection by connection.
So if consciousness is like this incredibly complex computer program,
Then to understand and replicate it, you arguably need to know every single line of code. Or, in the brain's case, every connection. This is where connectome mapping comes in. It's the science, the massive undertaking of mapping all the neural connections in a brain. We've seen progress. A fruit fly's brain connectome was fully mapped in 2023.
a fruit fly, okay, that's impressive, but the human brain, we're talking what, 100 billion neurons, 100 trillion connections.
Mind-boggling numbers, yes. Mapping a human brain at that level of detail is, well, it's currently seen as impossible. But, impossible for now is the key phrase in this field.
Yeah, I can barely keep track of my browser tabs. The storage alone for a human brain map and the processing power needed to run it.
Immense, truly immense. The computational demands are staggering. Moore's law suggests the raw power might be available in, say, a few decades maybe, but the actual requirements are incredibly difficult to quantify accurately.
We're talking huge numbers though, right? I saw estimates mentioning things like 10 to the 18 FLOTS, that's quintillions of operations per second, and petabytes, even tens of thousands of terabytes of memory just for the connections map. Those figures are in the ballpark of estimates, yes. A spiking neural network simulation, which is one approach, could require that kind of power. And storing the structural map, the connectome, could potentially take less than 20,000 terabytes. It's vast, but perhaps not infinitely out of reach anymore, especially for large-scale computing. So how do they even try to get this map? What are the techniques?
Well, one method is serial sectioning. You essentially freeze brain tissue, slice it incredibly thin, and then scan each slice electron microscopes, reconstructing the 3D structure layer by layer. It's painstaking, incredibly slow, and labor-intensive right now. But research is focused on automating this process significantly.
Okay, slicing up brains. Are there less destructive ways? Brain imaging?
Yes, using tools like fMRI and MEG to create functional 3D maps of brain activity. While current imaging tech doesn't quite have the superfine spatial resolution needed to capture every single synapse for a full upload, the resolution, both spatial and temporal, is improving incredibly rapidly. Who knows where it will be in 10 or 20 years.
And people are already trying to simulate brains, right?
Yeah.
Even if they aren't perfect copies yet.
Oh, yes. There's been significant progress in simulating simpler organisms. We have partial and in some cases arguably whole brain simulations of things like the C. elegans roundworm, the fruit fly we mentioned, and parts of the mouse brain. You also have big initiatives like the Blue Brain Project. They had very ambitious goals initially. Back in 2009, they claimed they could build a detailed, functional, artificial human brain within 10 years.
Did they?
No, not quite. The project later faced criticism for, let's say, mismanagement and somewhat overblown claims. But it still pushed the field forward in many ways.
And then there's the really out there stuff, nanobots. Tiny machines going inside the brain.
That's more speculative, yes. The idea is using nanobiotechnology, maybe tiny robots, that could potentially navigate the brain, map its structure from the inside, or perhaps even gradually replace biological neurons with synthetic ones. It's firmly in the realm of future possibilities, but it's being discussed.
Okay, so assuming, just for a moment,
Right.
that any of this becomes possible, mapping, copying, uploading, we hit that massive philosophical wall, don't we? If your brain gets backed up, is that digital copy? Is it really you?
The million-dollar question. Or maybe $1 trillion, given the potential stakes. It's often framed as a no and yes answer, really depends on your philosophical stance. Think about the copy and delete scenario, or maybe copy and upload, where the original continues to exist. Many see the copy as just that, a clone of consciousness, like making a perfect photocopy of a book. The copy has all the same words, the same story, your memories, your personality traits, but it wouldn't feel your continuity of experience. The original you, that stream of consciousness, would be gone if deleted, or would continue separately if not. The copy might even start making different choices immediately.
And this isn't a new dilemma caused by computers, is it? Philosophers have been wrestling with identity for ages.
Oh, absolutely. Way back in 1775, Thomas Reid posed the question, if all the atoms that make up your brain were gathered centuries later and reassembled into an identical thinking being, would that being be you? Would you be responsible for its actions? You can trace these ideas back even further. Augustine of Hippo in the 5th century, René Descartes in the 17th with his famous cogito ergo sum, I think therefore I am, arguing consciousness couldn't be an illusion. But then you have others, like Thomas Huxley, who saw mental experience as just an epiphenomenon, like the steam from a locomotive produced by the engine but not actually powering it. He thought consciousness arose from brain activity but didn't cause anything itself.
It really makes you question your own sense of self, doesn't it?
Yeah.
I mean, think about it. When you look in the mirror, is that really you from 10 years ago? Your body's cells completely replace themselves roughly every 7 years.
Yeah.
So in a way, are we all constantly being copied or renewed? Maybe a digital copy is just a more abrupt technological version of that same process. Maybe the continuous you is kind of an illusion anyway.
That's a fascinating and provocative line of thought. It touches on the Buddhist concept of anatta, or no self, and it leads us straight into what philosophers call the hard problem of consciousness, which is, how does purely physical stuff, neurons, electricity, chemicals, give rise to subjective experience? The feeling of redness, the pang of sadness, the taste of chocolate, these qualia. How does the physical become phenomenal?
Right. And there are different camps trying to answer that.
Broadly, yes. You have physicalism, which argues consciousness is an emergent property of complex physical systems, like our neural networks. If that's true, consciousness could be substrate neutral, meaning it doesn't have to run on biological wetware. It could potentially run on silicon or something else as long as the functional patterns are replicated. The mind is the information state.
But the alternative is?
Dualism. The belief in something non-physical, an immaterial soul or mind stuff, distinct from the body. If dualism is true, then simply copying the physical brain wouldn't capture consciousness because you'd be missing the essential non-physical part. This also brings up thought experiments like the philosophical zombie. Could you create something that looks, talks, and acts exactly like a conscious human but has no inner experience? It's just an incredibly sophisticated automaton. How would we ever know the difference?
Like the Chinese room argument, too. Just manipulating symbols according to rules doesn't equal understanding or consciousness.
Exactly. Does displaying conscious-like behavior prove actual consciousness? And then you have thinkers like Roger Penrose who propose consciousness might involve quantum effects that are specific to the biological structure of the brain, meaning it couldn't be replicated on a classical computer.
So, a lot of deep uncertainty. How do we proceed ethically if we don't even know if these digital minds would be conscious?
That's where Anders Sandberg's idea, the principle of assuming the most, PAM, comes in. It's a pragmatic approach. Basically, it says, given the uncertainty, we should assume that any sufficiently accurate emulation could have the same mental properties, including consciousness and the capacity for suffering, as the original system. And we should treat it accordingly, with moral consideration, just in case.
Okay, that makes sense. A kind of ethical caution, which leads us squarely into the ethical and societal frontiers. If these digital minds become a reality, the responsibility is enormous.
Huge. And it goes beyond just the legal question of whether AI gets personhood. That's a legal construct. The deeper issue is ethical. A core argument is that granting AI some kind of moral or legal status must not become a loophole for humans to dodge their own responsibilities for creating and deploying these systems.
And the ethics start way before we even get to sentient AI, right, in the development phase. Animal testing.
Yes. Developing this technology almost certainly requires animal experimentation. First invertebrates, then probably small mammals. There's the potential for causing pain or distress during the procedures, like mapping living brains. And then there's the even trickier question. Could the animal emulations themselves suffer? If PAM is applied, we have to consider that possibility.
And that connects to Nick Bostrom's concern, that Disneyland without children idea.
Exactly. The worry that we might spend vast resources creating these complex digital worlds, these potential digital afterlives, only to find out they're populated by non-conscious simulations. An enormous waste of effort, perhaps, that could have been used differently, a kind of empty spectacle.
A chilling thought. Building digital ghosts. It also makes you think about how we're already dealing with digital legacies, even without uploads. Like that ghost chip idea for social media. Facebook apparently had 50 million profiles of deceased users back in 2019, and that number's growing fast, expected to eventually outnumber living users. We're already seeing services pop up for digital end-of-life planning.
It's becoming a real issue. But there can be positive aspects, too. You mentioned a BBC documentary.
Yeah, it showed people coping with grief by essentially writing their lost loved ones into video games as characters. They found it genuinely therapeutic, a way to interact, to remember.
Interesting. But okay, let's get back to the potential uploads. If they exist, what rights do they have? Are they persons?
Exactly. Would they inherit property?
Right.
Could your digital copy decide to, pull the plug on your original biological self if you were suffering? How do you punish a criminal emulation? Can you delete it? Is that murder?
These are precisely the questions starting to bubble up. Some AI companies, like Anthropic, actually created a specific role for an AI personhood researcher in 2024. Though most major tech firms are staying pretty quiet on the official status of such hypothetical entities, there are serious concerns about potential digital human rights violations, too. Imagine governments or corporations running secret experiments on simulated minds or even entire simulated societies without consent or oversight.
And access. This technology would inevitably be expensive, at least initially. Does that mean digital immortality only becomes available for the rich, creating even bigger societal divide?
That's a major concern, yeah. The potential for exacerbating inequality is huge. And then there's the question that underlies so much of this for many people. What about the soul? If you believe human existence involves an immaterial soul, what happens to it in this process? Can technology create a digital soul, or is that fundamentally impossible? Does uploading separate the soul from the self?
So many layers. The sources really seem to warn against just blindly rushing forward with the tech.
They do. The consensus seems to be that unchecked technological progress here could lead to real injustice, could violate fundamental aspects of human dignity. AI development, especially something this profound, simply cannot be separated from its ethical and legal context. Preserving human reality, human dignity, has to be paramount when wielding this kind of potential power.
Okay, let's shift gears slightly then. A key enabling technology for all this, especially the emulation part, seems to be neuromorphic computing. Can you break that down for us?
Sure. Neuromorphic computing is basically technology that's directly inspired by the structure and function of the human brain. It often uses analog or mixed analog-digital circuits to mimic how neurons and synapses process information. The main goal is to create processors that are much more powerful for certain tasks, especially AI, but also vastly more energy efficient than traditional computer architectures.
So it's like building computer chips that think more like a brain. Is this the next generation of AI?
That's the idea, yes. If you think about AI generations, first gen was rule-based expert systems. Current gen is dominated by deep learning, which is great at pattern recognition, seeing, and hearing. But neuromorphic computing is seen as crucial for future AI generations. AI that can interpret context, learn continuously, and adapt autonomously in ways that are much closer to human cognitive behavior, overcoming some of the brittleness and massive data needs of current deep learning.
And are companies actually building these chips now? Is it happening?
Oh, yes, definitely. Major players are heavily invested. Intel Labs, for example, has their Loihi research chip. They're on the 5th generation now. It's a self-learning chip. Back in 2019, they built a system called Pahoiki Beach using Loihi chips with 8 million neuromorphic neurons. Their goal then was to scale up to 100 million neurons. A key feature is that these systems can learn incrementally, like humans, without catastrophically forgetting old information when learning new things. They've even shown it controlling robots in real time, like for playing foosball.
Foosball. Okay. What about IBM? I feel like they're always in the brain-inspired computing game.
They absolutely are. IBM has their True North processor. They described it as a supercomputer that fits in the palm of your hand. And the really stunning thing is its efficiency. True North consumes only about 70 milliwatts of power while performing millions of synaptic operations per second. Compare that to the human brain's roughly 20 watts. To get similar processing power for brain-like tasks with traditional supercomputers, well, one estimate suggested it would take huge systems consuming megawatts, possibly gigawatts of power. IBM's long-term vision, they call it creating a cognitive planet.
Incredible efficiency. Are there other big names involved?
Quite a few. DARPA, the U.S. Defense Research Agency, has funded a lot of work in low-energy neuromorphic computing. Companies like Neuromem Technologies focus on pattern recognition. Google, with its tensor processing units, incorporates some related principles. Qualcomm developed the Zeroth chip aimed at mobile devices, robotics, even medical applications, enabling powerful AI on devices with limited battery life. Samsung SK Hynix. Many semiconductor giants are exploring this space.
So the market is expected to grow.
Significantly, yes. All forecasts point to major growth in the neuromorphic computing market over the coming years, with North America currently leading the way in development and adoption.
And what kind of applications are we likely to see first from this, besides robot foosball players?
Well, beyond foosball, think about healthcare. Faster, more accurate diagnostics, maybe AI assisting doctors with treatment plans by processing vast amounts of patient data and medical literature in real time. Autonomous vehicles could become truly super intelligent. Imagine a car that not only drives itself but anticipates your needs, maybe even predicts your destination based on habits, and constantly scans the environment with brain-like efficiency for pedestrian safety.
And AI assistants, Siri and Alexa on steroids.
Pretty much. Assistants with vastly enhanced cognitive abilities, responding almost instantly, understanding nuanced requests, proactively adjusting your environment lighting, temperature, security based on learned preferences and real-time needs. Overall, the promise is for entirely new capabilities, potentially being, say, 10 times faster and much, much more energy efficient than current processors for these kinds of AI tasks. It could unlock brand new possibilities.
Okay, wow. We have covered a lot of ground today. A truly mind-bending deep dive into brain-computer interfaces, memory transfer, the quest for consciousness emulation, and this underlying neuromorphic tech making it seem, well, less like pure sci-fi.
We really have. And as we've highlighted throughout, alongside the incredible technological potential, there are these profound philosophical, ethical, and legal questions that just loom larger and larger.
Yeah.
What is consciousness, really? Who owns a digital mind? How do we possibly ensure human dignity and maintain human responsibility in a future so deeply intertwined with potentially conscious or near-conscious AI?
Yeah, that's the core tension, isn't it?
Yeah.
This relentless drive for technological progress bumping right up against the fundamental need to figure out what makes us human and how to preserve that.
Absolutely. Which leads us to the final thought, maybe for you, the listener, to chew on. If our consciousness can truly be replicated, if it can live on digitally, how does that fundamentally change everything? Our understanding of being alive, of loving, of suffering, and perhaps even more unsettling, will these future digital selves evolve? Could they become something entirely new, forms of being that diverge so much from us that they challenge our very definition of humanity? What really stands out to you from everything we've discussed today?
So much to think about. We really hope you enjoyed this deep dive into digital immortality. What are your thoughts on mind uploading? Seriously, do you think a digital copy of you would actually be you? Let us know. Share your insights, your questions, your concerns. Join the conversation in the comments below. We'd love to hear what you think. And hey, if you found this deep dive fascinating, if you want to keep exploring the cutting edge of science, technology, philosophy, all that good stuff, make sure you subscribe to The Deep Dive. And maybe share this episode with someone else you know who loves getting up to speed on complex topics quickly but thoroughly. Until next time, keep digging deeper.